guest do we have today? All right, good morning, ladies and gentlemen. Today I have brought in two very special guests. We have Delia Moore and
Why does that sound evil? An evil introduction.
You guys have met both my sisters before. They came and talked to you. So today we're going to be doing this lab, Wave Player.
That's right.
And we're going to start off by getting the data to calculate the speed of our wave. So for this, we measured out 8 meters. Oh, Mr. Boy can measure it out.
So Delia, what is it we're going to be doing here?
We're gonna be trying to figure out the speed of our wave.
Well, send a pulse across to the other side.
Not alone.
Whoa. So it takes a certain amount of time. That's 8 meters. So who's got the stopwatch? All right, you say on your mark, get set, go, and then Delia send it, okay?
On your marks, get set, go.
Boom.
Time.
1.36.
1.36 seconds.
1
No, that's actually good.
Look at that restoring force. You got it?
And now, this line is 4 meters. No.
Oh, yeah.
Now we're going to do the same thing. How much time does it take to go 4 meters?
On your marks, get set, go. 1.45. I think the...
Which one looked faster? Which one looked slower? Here, do that again.
That one looks slower. On your marks, get set, go.
Dang. You got to whoop that sucker, girl. Whoop that sucker.
More, give it more. Come on, with the same oomph. With the same oomph.
Okay, on your marks, get set, go.
Go.
1.35.
All right, sweet.
Ooh, what do you guys
So boys and girls, y'all writing this stuff
Look
down?
at that. Okay.
All right, so now back to 8 meters, okay, Dee? It's all a matter of degree. Okay, now what are we doing?
Okay. Go ahead, Dee.
Frequency.
So we're going to be changing the frequency for low frequency.
That's what I mean.
Yeah.
Okay, now you're messing it up.
Okay. I'm not messing it up.
Okay, so this is a low frequency wave. There's a high frequency wave. Now what is frequency?
It kind of seems like frequency is like how fast she's going.
It's how frequently you make a wave.
Yeah.
Well, we've gotten a workout open here.
So low frequency
Not very many.
and high frequency. Okay, so think about what those two things are, and what I want you guys to do is we're gonna go ahead and draw what that wave looks like, right?
Yeah, and you could pause the video, go back and pause the video for a low frequency wave, low frequency, and then high frequency. Steph, why don't you do it? Okay, her turn. Now you do low frequency. Oh baby, that's a low frequency right there, and then high frequency. I wish school was in session. You kids could be playing with this.
Okay, so my wave is not very good, but this is what I drew. Do you guys have something similar? Hopefully.
Which has a longer wavelength, higher low
Wavelength.
frequency? Not sure what wavelength is. Okay, what's next?
Okay. So time for 10 cycles. So we're gonna make the low frequency wave and measure the time it takes to move your hand back and forth 10 times.
I would like let me go first and then be like stuff. You know what I mean?
Is it also when the 10th wave reaches me?
Well, no, it's not traveling. It's
just
how fast she's making them.
So it'll be like 1, 2. Okay, make it. You start whenever. I'll just keep going.
2, 3, 4,
Ah!
5, 6, 7, 8, 9, 10.
5.42 seconds.
Now, is this good enough? Is that
Yeah.
wave good enough? Okay,
Yeah.
give me going. What was it? What was it, Steph?
5.42 seconds.
Okay, so the time for 10 cycles for our low frequency was 5.42.
All right, now a high frequency. This is going to be.
Okay.
Was it helpful for me to count stuff?
You watch your hand, and whenever you want to go, go.
2.33
Whoa.
Wow!
2.33 seconds? Yeah.
Thank you.
Yeah. I was just, it's easier for me to just pick at the starting point. And it was like 1, 2, 3, 4, 5, right, like that.
Yeah. But you're going
You guys catch that? You guys see how she count that?
How did you do it?
1, 2, 3, 4, 5. Because it's a time for one cycle, which
Yeah,
is like
where does the cycle start at,
1,
B?
2, 3, 4, 5, 6.
Yeah.
Because if you go left and right, it actually makes two waves. So
Well, it makes a wave on one side and the other. It makes, you got bumps on both sides. See, here's equilibrium, and there's a disturbance in equilibrium. See, so if you move your hand back and forth, you get a bump on both sides of equilibrium. I like that. What happens if you move your hand back and forth just a little bit? And what happens if you move your hand back and forth big?
So the height is different, right?
Yeah, and the little ones didn't go as far as the big ones, right? Okay, what else do we have to do?
Okay. All right, so it looks like we have all the data we need to do our calculations.
So, ladies, I think we're done.
We are.
Woohoo!
Okay, thank you so much for your service today, ladies and gentlemen. And we're good to go.
Here we go. Go.
All right, so welcome back. We're gonna go ahead and do our calculations. First one says, use the data at the top of the page to find the speed of the wave for the 8 and the 4. So throughout this whole time, I'll do one of them and you'll do the other one. Okay, so we'll start with the 8 meter one first. So we'll say velocity equals distance, which was 8 meters, divided by our time, which was 1.36 seconds. Oh, I said 0. 1.36 seconds. 8 divided by 1.36, and I forgot my meters right there, seconds, and I get 5.88.
5.88 meters per second.
8 meters per second. And so you guys do the same thing, but you guys do it for the 4 meter one.
All right.
Okay. All right, so find the period of your waves by dividing the time for 10 cycles by 10. Okay, so the time for 10 cycles for the low frequency one was 5.42. So that's just going to be the time for one is just going to be 0.542.
Yep, it'd be 5.42 divided by 10, which is 0.542.
Okay, do the same thing.
And that's going to be seconds per cycle.
Oh yes, I forgot about that first cycle. Because it's 10, it's time over cycles, seconds per cycle.
You do the same thing for the low frequency.
Do it. Okay. Use the period to find the frequency of
Oh, you
your
know
two
what?
waves.
You know what? We did that backwards.
We did?
That's, I'm sorry. That's the low frequency in that. So we just did the low frequency. You did the high. That's my bad. Not
Yeah,
yours.
right here, right? So we're low here, good?
Yep.
And then they do the high.
do the high.
I didn't even catch that you said it like that.
my
Okay,
bad.
so then use the period to find the frequency of your wave. So again, we'll do the low. So we'll just do 1 over the time. I'm sorry, the period, which is 0.542 seconds per. Do you just say cycle like that when you do it, Mr. Bogan?
It's seconds per cycle. Yeah.
Yeah,
sure.
but cycle, do you write cycle like that? Cycle's
Yeah.
kind of like, it's hard for me
Well, I
to
do
write.
SEC or CYC.
CYC, okay. 0.542, and I get 1.85. And our units here are going to be cycles per second.
Yep.
SYC over. So for every second, you're going to have 1.85 cycles.
Yep.
Almost 2. Okay. And you guys do the one for the frequency, for the high frequency. Oh, right here. Use whatever you got from right there. Okay. All right. The velocity of a wave in a medium doesn't change if the frequency changes. Huh. So even if you go faster or slower, the velocity stays the same.
That's right.
We can use the velocity, period, and the frequency, period, and the frequency, to find the wavelength. Aha, that's this thing right here.
Yep.
Of our two waves. Use the speed you calculated on the other side. Okay, so here's our speed. We're going to do our low frequency one.
No, that's the 8 meters. We'll use
Yeah.
that. 8 meters.
8 meters?
5.88.
Oh, I see. So it wants, low for 8 and low for 4. High for 8, high for 4? Is that the idea?
Yeah, what
Okay.
we're trying to find out is how long each wave was. Remember, if you moved your hand fast, there were a bunch of them
Oh,
close
like this?
together.
Yeah. So
Yeah.
we're trying to figure out from here to here.
Yep.
Okay. All right, so for the low frequency for the 8, because I did 8 right here, it's going to be 5.88 meters per second divided by our frequency, which is going to be 1.85 cycles per second.
Yep.
Okay, I like how you staggered them like that for me. 5.88 divided by 1.85, and I get my wavelength is 3.18.
Yeah, just call it 3.2 meters.
3.2 meters. Okay.
All right.
Oh, I didn't see this is a different equation right here. Okay, I thought this was the same thing.
Well, let's find out. This one uses the frequency, which we have here. This one uses a period, which we have up here. So
Okay,
let's do
go
both
look
of
it
them.
in. So we've got our velocity, which again for so instead of the low, it's just for 8 versus 4. Is that's
No,
what
we're doing it all for 8 meters.
Oh, I see. Okay. Okay. So that times the period, which is
0.542.
542. And what do you guys think is gonna happen? Will it be the same? See, I can't. I really struggle with writing that. 5.88. Will it be different? 0.54. Oh, 542. Forgot my 2 there. That's a 2. 2, and I get look at that, 3.2.
Also 3.2 meters per second.
Okay. So you guys are going to now do the same thing, but for the high frequency, and will they use the they use 8 for all
Yeah,
of it?
because when the girls were doing the fast and the slow, they were at 8 meters apart.
Yeah.
So
yeah.
we'll use
oh,
that.
that's right. I remember now. Okay.
Yeah.
All right. So calculate the wavelength for the fast and slow again using this velocity right here because we're talking about 8 meters per second. 8 meters. I'm sorry. Okay. Okay. So compare the length of the waves you just calculated. With your drawings on either side, do they match?
Okay, so we'll have to wait for them to calculate these other ones and then compare them with what you've got drawn.
And you can kind of make a prediction by looking at what you've got over here. You know, well, not a prediction, but what do you have here? Does it match with what your calculations say?
Okay? Is good.
Ready? Oh, okay. So, what was I saying? Oh, yeah. Okay. So, since we're done with our calculations, let's go ahead and jump right into what's going on here. Let's talk about the parts of the waves and all that jazz. So, let's start off with this question: what was making the waves?
Well, they didn't come out of nowhere.
Right? It just magically appear, right? My sisters were making the waves, right?
Yep.
Okay. And
They were the source.
what about the waves could you control? What couldn't you control? Well, you could control how fast it was going, right? The frequency.
You could move how fast you moved your hand.
Right, the high and the low. What other things could you control?
You could move your hand a little bit
or a lot, right?
Yeah.
That changed the height of it, okay. And then we also changed the length, right? We went from 8 meters to 4 meters.
Yeah, but if you stay at just one, let's say 8 meters, because the waves are much more interesting, that's about all you control.
Yeah, okay, so what can't you control? Well, should we answer this question?
Well, no, we'll get to that in a minute.
Okay. Were you doing any work?
What is work?
Well, work is force over displacement.
Were you
Were
exerting,
you exerting
a
a
force?
force over a certain amount of displacement?
Absolutely.
We
Some
sure
work
were.
was done.
So work was done. How was your work expressed in the wave? Doesn't work do energy?
Yeah, if you did a little bit of work, what would the wave look like? If you did a lot of work, what would the wave look
Yeah, it's a
like?
little bit of work. It goes out, oh. Okay, a lot of it work. The wave's like, whoa, right? So it displays itself in, I guess, like how big the wave is, right?
Yeah, I just thought of something.
Huh.
If you do a little bit of work, if you just move your hand back and forth a little bit, you get little bitty waves.
Oh, so cute.
If you do a lot of work, you get big waves.
And you can see how it manifests itself in that wave. Your energy is transferred into that wave. Okay?
Cool.
Cool. Good thinking, Mr. Boykin. Oh, it says wave parts right there. We'll get to that in a
We'll
second.
do that in a minute.
Okay, a wave is a disturbance in a medium that travels from a source.
Yep. There has to be a
So-
source, there has to be a medium. The medium here was the slinky.
Yeah. Okay. And what was the source? It was my sister.
Whoever was
Right.
shaking the
D.
slinky.
D. Okay. Wicked. A question I have is a wave is a disturbance in a medium. Now, could a medium also be like the air or
Absolutely.
something else? Okay.
Yes. Or
Okay.
water.
Or water.
Yeah,
Okay,
any
so-
number of things.
So,
Waves.
but
The
today,
earth,
But today it was
the
just
slinky.
Just a slinky. Okay. What happens to the speed of the wave when the slinky went from stretched 8 meters down to 4 meters? Where's my? Oh, it's right here. Oh, I have some of the. I do actually have the answer key for this one. Okay, so the speed went from 5.88 meters per second to from 6 to 3 basically, right? Cut in
Yeah.
half. So
And why would that be? It was slowed down. Why? What's the difference in the properties of the slinky when you've got it stretched out 8 meters compared to when you have it stretched out 4 meters?
does it have to do with the restoring force?
It has everything to do with
Yeah.
this restoring force. It's like pulling on a rubber band as far as you can make it, or just pulling it halfway. There's more restoring force pulling it back.
Okay, so what happened? The velocity of a mechanical wave is determined by the medium carrying the wave.
Okay, this is very important. This is probably the most important statement here. It's how do we change the speed of the wave? We stretched the slinky more or less. We changed the properties of the medium.
Yeah.
Moving your hand faster or slower has nothing to do with it.
Doesn't change the velocity. So you can either change the, like you said, the stretch, the length of, on the force that you're putting on the slinky, stretching it out. Not this way, but the stretching it out. Is that what you said, Boykin?
Yeah.
Or for example, you can put it in some water, right?
By changing the properties of the medium.
Yeah, exactly. Okay. Okay. The source of a wave determines its amplitude, period, and frequency. Oh, we forgot to mention period. That makes total sense, right?
Yeah.
Because frequency and period are related. What's amplitude?
What is, oh, there it is right there.
Amplitude is the maximum displacement from equilibrium. Okay. And I think that we've got that on the next few slides here. So we'll come up to that in a second. But we know equilibrium. Oh, we put away the slinky.
Yeah, well, we got a slinky right here. The slinky is at equilibrium. And so a small amplitude is a small disturbance from equilibrium. Okay, the maximum displacement, I moved my finger this far over, got a little bitty wave. If I move it farther, that's a larger displacement for the equilibrium.
Nice. You don't normally use this one to explain this, Boykin? You probably don't need to.
Absolutely. I
was
use it
gonna
all the
say,
time.
this
That's
is
why it's
like-
up here.
This is a great little guy.
That slinky took 2 hours to put up.
Oh my gosh. Okay. Oh, play with this. Okay. Oh, I forgot to. Here's what I'm gonna have you guys do. You guys are just gonna click on the PhET simulation above. I'll probably call it like Slinky Sim or something, or Wave Sim. And I want you guys to play with it. Use the side view, push button on the pipe to start change frequency and amplitude.
What it does is it's got a faucet that drips water onto into a sink, and the waves spread out from where the drop hits, and you can change how big the drip is. You can make it bigger or smaller. That changes the amplitude. Oh, check this out.
I do. I figured out how to get over there and get it.
And then
Okay.
side view here on the bottom.
Okay, so side view right here. Okay, so top is the top like that.
Yeah.
Side view is like this, okay? And what does it say to do to push go right here?
Yeah.
Oh, totally groovy. Look at that. And I can,
You can play with the frequency and the amplitude up here. You can look at it from different points. You can send a single pulse. You can send a bunch of them and play with it. See what you can do.
oh, groovy, cool. Okay, I'm gonna push pause. Oh, and you could go slow if you want to. Okay, you guys get the point. Okay, we'll link that in for you guys. Go ahead and play with it on side view.
Play with this.
Push the button to start the water.
Play with this.
And change the stuff around. Okay, wavelength is the horizontal length of one cycle. We saw that earlier, right?
Well, this is the definition.
Yeah.
And the symbol for wavelength is the Greek letter lambda. Lambda, lambda.
Lambda. Okay. Okay, so this is the picture I was kind of waiting for. So amplitude, again, if this dotted line is the equilibrium, and Boykin showed us when he was playing with the ceiling slinky that, that displacement from the middle, that's the amplitude. And the wavelength is from crest to crest.
Well, it's from one spot on the wave to the same spot on the wave. Notice that there's two wavelengths here on this diagram. So here's where it starts up. That starts the wave. Here's where it starts up again. That's one wavelength. And you can change that. Look at Satan's sign. You can change that wavelength anywhere along there, like that. By the way, there are two wave parts on here. That bump on the top is called the crest. The bump on the bottom is called the trough.
Technical terms, okay.
Yeah.
And again, what things can we change? We can change the source. It can change the amplitude, the period, and the frequency. However, the medium has to do with the velocity.
Yep.
Okay. Which we can also change the wavelength then too, right?
Yep. By changing the velocity is fixed, but you can make your hand go faster or slower.
Yeah, and depending on the frequency, that affects the wavelength.
Yeah.
Okay, the source and medium together interact to produce the wavelength. Okay,
Yeah.
So here's the source, the frequency. The medium is the velocity, and
Yeah, the source produces the frequency. That's what you're doing when you're. If you were here, you'd be playing with these yourself. And the medium, the slinky, determines how fast it goes. And so what this says is if you're shaking the slinky back and forth at the same speed at 8 meters, you'll get one wavelength. If you shake it back and forth at 4 meters, you'll get a smaller wavelength because the velocity is smaller.
okay, bada boom. When you sent waves across to your partner, what was traveling? Good question.
Yeah, can you reach this and send a pulse?
Okay.
Okay, hold on. Now I've got a string right here. Yeah, go ahead, send a pulse.
You ready?
Yeah. All right, so that wave is going back and forth, but the slinky's staying in the same spot. It's not going anywhere. So what was traveling?
So, let me see what you got on your next slide here. Okay. Waves transfer energy, and waves transfer momentum.
So waves are transferring energy that you put in when you do work through a disturbance through the medium.
Exactly. Let's see. The energy transferred by a wave is proportional to its amplitude.
The bigger the bump, the more energy. The more work you had to do making that thing, the more energy that's going to be transferred.
That makes sense.
Yeah.
Okay, what was the relationship, the relation between the direction you were moving your hand and the direction the wave traveled? Well, when I moved my hand, the wave went up with me, right? Is that the idea?
Well, if I send a wave down here, I'm moving my hand back and forth like this, and the wave is going that way. So I was waving my hand perpendicular, and the wave was traveling down the slinky. So
okay. So, that's actually different than what I was thinking. Absolutely. So, when we were doing our lab, we're moving our hand up and down if this is the floor, but the wave is traveling that way. So that's that perpendicular.
That's right.
Right there. Okay. And then I've got our video. We thought we were prepared. Not prepared.
This is very short.
This will give you guys some time to just, get some popcorn.
In a longitude.
Let me go full screen here. And I'll start over.
There's two kinds of waves.
Go ahead, Brian.
Go. No, turn on.
Longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels.
Stop that wave. Yeah, in other words, if I pull on this string and pull it back and make it go this way, I can get a longitudinal wave that goes back and forth down the spring just like this. That's not...
Longitudinal waves are also referred to as compression waves.
Sweet.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
this is what we were doing in the lab today.
Yeah.
Show that again. So there's two kinds of waves. There's
In a
transverse.
longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels.
So the waving is back and
Longitudinal
forth
waves
this
are
way.
also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Sweet.
That makes sense. All right. Done with you we are. Okay. And action. All right. So transverse waves oscillate perpendicular to the direction of travel.
That's what we were playing with today. Were transverse waves.
Yeah, so we move. We were playing, on the ground, moving the waves like this, moving our hands up and down, and then the wave travels that way. Whereas longitudinal, you're applying a force that way, and the wave is traveling that way.
Yep.
Okay, I think your next slide is longitudinal waves oscillate parallel to the direction of travel.
And we'll talk more about longitudinal waves tomorrow.
Okay. Transverse waves that oscillate in one plane are polarized.
Now, what the deuce does that mean? You're down on the floor, making the slinky go back and forth. The plane of oscillation was horizontal. The floor kept it
along
flat.
with the floor, right? Just like this. This is it. This is the plane from here to here.
Yep.
Right.
Now you could make your hand go up and down and make a vertically polarized.
Okay.
But this is just a term you hear, polarized or polarized sunglasses or stuff like that.
And will
This
we
is-
get more into that later, or is this all we're gonna
Yeah,
do?
a little bit.
Okay. All right. So the idea is just one plane, right? Just this
Yeah.
way, or just this way, or
Yeah.
whatever. Okay. Can longitudinal waves be polarized? Well, are longitudinal waves, are they moving in a plane? This is what a plane looks like, right? So this could be a plane, right?
Yep, that
And
is
then
a plane.
can I do it up and down here?
Well, no,
Okay,
you
I-
can't. You can,
It'll
but
get
it
all-
won't go because
okay.
of the strings.
Yeah, or it would be like this, right?
But if you move your hand back and forth like this,
Yeah. Oh, come on. Okay, like this.
yeah,
Okay, these are my longitudinal
Longitudinal.
waves. There's no plane there, right? It's
Nope.
just forward.
it just goes down the slinky. So
Yeah, so the answer is
No.
no. All right, so your homework tonight, go ahead and read page 422 through 425, exciting stuff.
Yeah.
And you're gonna do page 448, concept number 3, and then problem number 3.
there are two number 3s on that page. So on your mark, get set, go.